Okay, this is my attempt to draw a picture of my laptop with a cable that is connected to a plug that I would plug in to the main socket on the wall of my room. So let me write this out. This is the mains socket. Okay, it's supposed to provide an AC voltage with an RMS of 240 volts. So this can be either in the UK or in Singapore, for example. And we understand that this is supposed to be R and S. It doesn't really matter for this example, I think. And it's an AC with let's say a frequency of 50 to 60 Hertz. I'll take it to be 50 Hertz. Okay, so that's my typical mains socket in the house. If I need to plug my plug, right? Okay, this is my plug. I need to plug my plug into the socket, right? To use my laptop. My battery is not really charged at the moment. Okay, so that's my laptop. It says that physics is fun, and that's my keyboard. Now, why do I need to have this little thing down there? Right, if you have seen a laptop before, you see this chunk of rectangular block in the middle of the cable. And you don't need to just see that for laptops. You might have seen this for other kind of electronic equipment, like maybe a charger, a phone charger, or other things. Now that thing there is usually called, let's see, what is it called? It's usually called an AC adapter. Write this down. Oops. It's gone. Okay. AC adapter. Now when I look more closely at this thing on my cable, I see some numbers and some words. Okay, let me write down what I see. I see this word. I see the word 65 watts. Okay, we know watts is for power. I see the word input. I see the numbers 100, 240. V for volts, I guess. And I see a squiggle here. And I see 50-60 Hertz. Now I'm guessing that the squiggle here means the same as AC. Little squiggle there. And it says 1.5 ampere. Okay. Oh. And then below that, there's this word output. And it says 19.5 volts. Then there's a line. Then there's a dashed line. 3.34 ampere. Now, I'm guessing that the straight line here means direct current, means DC. In other words, this adapter would convert a voltage that is maybe either 100 or 240 volts or in between, and going at changing at this frequency, and maybe up to 1.5 ampere. It would convert this description, an alternating current of this description, to an output voltage, which is a direct current, which just goes in the same direction and maybe stay constant, doesn't keep changing, and that has a voltage of 19.5 volts, and that can give a current of 3.34 amperes. Now, you understand that this kind of figures, this kind of numbers refers to a rating, which means that it doesn't. I think it has to give 19.5 volts. I think that's fixed by the design, but it probably doesn't have to give exactly this amount of current. For example, if I unplug this part, if I unplug it from the laptop or whatever device, the voltage should still be there, but there would be no current flowing, obviously. Okay, so this is a rating. These numbers must be for a rating, which means that it's the maximum kind of current it can take, and that is kind of determined by this number here, 65 watts, which is the maximum power it can take before it. If you give it too much power, if it takes too much current, for example, it might just get very hot and burn up. Okay, now, and what you'll find is that not only for the laptop, but in many electronic appliances, these appliances would often need DC. It would often need a direct current to operate. It can't work on the alternating current directly. Okay, but the current, the power voltage coming to our main socket, coming to our house from the power station, is always, as far as I know, is always alternating current. The reason is more or less what we have been through in the past few videos. The reason is because it's the practical way to generate voltage using an AC generator and maybe a steam engine, and it's a practical way to transmit this electric power through long distances using step-up and step-down transformers to save energy loss through the long distance cables. So we kind of understand why we need AC to come to our house, and we've not really learned much about electronics, so it's not so obvious at the moment why we need DC, why we need direct current for electronics. But that's okay for this video. Let's just assume that we really need direct current to run the electronics. Now, of course, I could have used batteries. We know that batteries give direct current, and laptops have batteries. But batteries run out and you have to charge it. So the most convenient thing, therefore, is to have this AC adapter that can convert an AC to a DC. Alright, so it's a really useful thing. Now, what I'd like to do in this video is to briefly explain how an AC can be converted to a DC. Okay, to properly convert to a perfectly smooth and constant direct current, it is a little bit complicated. So what I'm just going to do is to talk about a very simple setup in which I can convert it to current in one direction, but it's not going to be a perfect DC, but it's a start. Right, and the method is really quite simple. I have to use something called a diode. Now, many videos ago, I've talked about a diode. Now, if you can remember that a diode is a device that can only allow currents to go in one direction. If you have actually seen a real diode before, it just looks like there must be many shapes and sizes. So if you look at it, it can be either inside a chip, which is just rectangular, or it can be a little tube, okay, with maybe a line on one side and some wires connecting to it. Okay, and then if you or the symbol as the symbol, the circuit symbol in the circuit symbol is usually represented this way: a triangle with a line and wires coming out. And if you remember, the action, the function of a diode is that it only allows current to flow in one direction. So current can flow this way, but currents cannot flow the other way. So if I try to connect this to a battery the wrong way around, no current will flow. So let me do something very simple. Let me just connect this to an alternating current. So if I simply I'm going to use this circuit. If I simply connect this directly to an alternating current, let's say this could be my mains power supply. I'll simply connect this to an alternating current. This AC voltage will try to push a current through the circuit, and this current would keep changing direction because it's AC. But the AC voltage can push a current only in this direction. Only in this direction. When it reverses direction and try to push a current the other way around, the current won't flow. It will be blocked by the diode. Alright, so that's what happens. So you know what AC does, right? It keeps changing direction. So current flows one way and then the other way, and then one way and then the other way. But if you connect a diode in a circuit, then current can flow one way, but when you try to flow the other way, it's stuck. Then there's no current. And then when it flows, when the voltage goes this way again, there'll be current. So what would happen then is that you have a current that flows for a short time, and then it tries to reverse but it's stuck, and then it flows again for a short time, and then it tries to reverse and it's stuck again. So it flows, stop, flows, stop, flows, stop, flows, stop. And that is basically what would happen if you connect a diode to an AC voltage. So let's try and plot some graph. Let's say I look at my AC generator. Okay, now the voltage coming out from here, I'll call that V. Let's say that the current flowing through this I, and the voltage generated by coming out from the mains supply is V. So I'd like to plot a graph of that, and I would like also to plot a corresponding graph for the currents. Okay. So the voltage just looks like a sine curve, goes up and down. So that's the voltage coming out from here. It's like a force trying to push the current through, an electromotive force. Okay, so now I'm going to try and draw the graph for the currents. So I'm going to draw this dashed line so that I get the timing right. Okay, now suppose that this positive direction is this direction. that's a positive direction. No, that might be misleading. Wait. I want to show a positive direction, but I don't mean that this is the positive pole, because it's not like a battery. It will keep changing poles, if you like. Right, what I'll do is this. I'll draw an arrow here to say that if the current flows in this direction, I call it a positive direction. If the current flows the other way, I call it a minus direction. Okay, so it's just a direction thing. Right, so when the voltage is positive, it means that my positive pole is here and the current will flow this way. When it's negative, it means that the positive pole is on the other side and current will try to flow the other way, but it can't, of course. So therefore, if I plot the current graph, then when the voltage is one way, the current would flow. Okay, let me use a different color, maybe a yellow color. There, current will flow. Now, when the voltage reverses direction and try to push the current the other way, the current gets stuck, it can't flow. So there would be zero current here. Okay. Although in practice there might be a tiny little bit for a real diode. Okay, but I'm just going to take it to be zero. And then when the voltage reverse direction again, the current can flow again, and when the voltage reverse, it gets stuck again. So that's what the current graph would look like. It sort of flows, stop, flows, stop, flows, stop. If you look at this, obviously the bottom part of what should have been or might have been a sine curve is cut off. So it looks like half the time the current is cut off, is just zero. So the current is obviously flowing only for half the time. Or you can think that what would look like the normal sine wave, alright, get cut into half. So you only get half the wave. Alright, and because of this, there is a name. The name given to this method of turning an AC to a DC, of turning an alternating current to a direct current, is called a half wave rectification. So half wave rectification is this method of turning an AC to a DC in which only we get only half the wave.